Hey, welcome to Doc Onco's Physics. My name is Keith Onco, and today what we're going to be doing is taking a look at some of the properties, or one of the properties in particular, of light waves. And that property happens to be the diffraction of light waves. Back when we looked at sound waves, we might have looked at how these waves can bend as they hit a surface or hit the edges of a surface. And when an object, or when waves hit the edges of a surface, they bend, and that bending is called diffraction. But before we get into that, what I wanted to talk about is how waves and particles can be different. Okay, up in the top of the screen you see a slide called the wave nature of everything. Well, when we think of particles, particles have mass, particles have charge, they can have spin, and they can carry energy. Those are four of the characteristics of a particle. When we think of waves, waves have attributes like frequency, wavelength, amplitude. They can carry energy as well. But one of the things that a wave does that a particle doesn't do when we observe them interfering with each other is that they can add constructively and they can add destructively. And we see this every day, or we experience this every day in life, although we may not realize just why we experience it. So one of the particular things that we're going to look at as far as a characteristic of a wave is that the fact that they can add constructively and they can add destructively. So if I take and slide down here a little bit, if I had two, whoops, let's go to my pencil there. If we had two different waves here, let's look at this wave up here and this wave down the bottom here. And as you can see, both of those waves are about the same amplitude, and they are both called what's in phase with each other. So the peaks are at the same position and the troughs are at the same position if we had a timeline along the bottom here. If this was time along the bottom, for every period of time that you looked at a wave, both waves would have exactly the same amplitude. Okay. When I add these waves together, they add up in a way that's called constructive interference. So if I add the top wave up here and I add the bottom wave down here, what I'm going to get is the wave to the right, the red wave to the right, and this is called constructive interference. You're just going to get a much larger wave that looks like the other two waves, but the amplitudes and the troughs are the peaks and troughs are greater, and so the amplitudes are greater. If you look to the right, we have, again, very similar waves, right? We have the top waveform looks very much like the top waveform on the red side, but the bottom waveform, if you'll note, is out of phase or is out of sync with the top waveform, right? So if I look again, if I look along the time line down at the bottom in the x coordinate, if I look at one particular position here, say right here, okay, the value of this wave, the top wave, if I add that to the value of the bottom wave, what I'm going to get algebraically, if I add them together, I'm going to get 0. Okay, that's a bad 0 there. I'm going to get 0. If I add this trough with this crest down here, what am I going to get? I'm going to get 0. So all along with these two waves, when I add these two waves together, I'm going to get an answer of 0, or I'm going to get a flat line, which is depicted over on the right hand side here. So waves add together. Waves can add together to make larger waves. Waves can add together to make smaller waves. And that's very important in this thing called diffraction. So let's just slide down here a little bit. And we got a couple of examples of diffraction. On the left-hand side of the screen, we have a ball that's been placed on a table or whatever it might be. And we have some light waveforms that are coming in from the left, and they are hitting the ball. Now, some of the light waves simply get blocked by the ball. But the light waves at the edges of the ball, right, right there, I should change the color here to something that is more visible. The light waves at the edges of the ball, okay, they are able to get by. But notice what happens to those light waves when they get by. The light waves were flat, now I got to change it back to black, were flat as they approached the ball, but when they hit the edge of the ball, the light waves became curved. Okay, and so what you end up with is, past the ball, you have one set of light waves on the bottom side, you have another set of light waves on the top side, and they are curved. Well, what happens is these curved light waves expand outwards as they go out into space, and they meet right there, right? They meet constructively right there, they meet constructively right there, and they meet constructively right there. Sorry, I'm making these circles not the greatest visually, but you can see where we have bright waves out here somewhere, right? Out here, the only reason we have these brighter waves is because they are adding constructively together. Now you also notice that there are some areas where the waves get fuzzy or almost go away altogether. That's where they are adding destructively together. Okay, so they can add constructively and they can add destructively. So just the same way as a light wave can hit the edge of a ball, like the example on the left here, right? We also have another example over on the right-hand side where we have light waves that hit an opening here, and you may not be able to see the opening all that well, right? But the opening is right in there, and they hit the opening. Now the opening happens to have two edges, right? An upper edge and a lower edge. Well, when these light waves hit the edges, they're again going to bend on either side, and they're going to create the patterns that you see to the right of the opening. And they are these curved patterns. So they go out like this. And the further out from the opening, the wider they get. Okay, and so we have these waves. Now, this is known again as diffraction. It's the bending of light. Okay, so let's take and slide down a little bit here. So what happens, we see what happens if we have more than one source on the left-hand side up here, right? So I have initially just a source over here, but when it hits the ball, it creates two separate individual sources. And that's what we want to look at now. So let's look over on the left-hand side of the screen here. What I've got is I've got light rays that are coming in from the left-hand side here, and they hit these openings S1 and S2. Well, what happens is with S1 is going to create some semicircular wave patterns, right, like this. And S2 is also going to create some semicircular wave patterns. Well, what happens where these wave patterns intersect with one another? Well, what happens is we get constructive and destructive interference. The green lines here on the chart show where there are minimums and maximums for the waves. Okay, so where a crest meets up with a crest, right? Say at this point right here, let's see, at this point right here, at this point right here, we're going to get maximums. Okay, where a crest meets up with a trough, which would be, let's see, crest and trough. Here's a crest, here's a trough meeting right there. Crest and trough meeting right there. Should change the colors here. Change that to red. Right there. See, crest and trough meeting right here. Okay, and a crest and trough again meeting right here. Okay, these are called minimums because crests and troughs are meeting, and they are canceling the light waves out altogether. And so, if you had a screen that was over here, okay, what you would get where it would be dark and light areas on the screen. Where we have maximums, I should change that to blue maybe. Where we have maximums, what's happening is the crests are meeting together. So we have crests meeting together here, we have crests meeting together here, we have crests meeting together here. And so we get, when two crests meet together, we get more light. Right? Just like in the diagram I showed up here, when the crest and trough meet together, they cancel each other out. When crests and crests meet together, right, they add up and we get a larger wave. Okay, well, this works with light as well. So we can see sort of a pictorial representation of that here. To the right in this diagram, right, you can see the actual wave fronts, and where the waves meet together, right, these are crests meeting together, right? And where you see dark areas, those are typically where crests are meeting troughs. Over on the very right-hand side, what we have is a diagram that you would see if you took something called a diffraction grating, and a diffraction grating is really nothing more than what we have on the left-hand side of the screen, but it's got more than two openings. It typically has thousands of openings, all right? But it does the same thing. It allows light through, and these light waves are going to interfere with each other. Now, over on the right-hand side, the light waves are interfering with each other, and what they do is they create all these patterns of dots on the right-hand side. Okay, the dots are where we have maximums, right, where the waves are adding up constructively, and the dark areas in between the dots are where we have minimums, where we have total light destruction. Okay, so that's diffraction. Here's a better, maybe a better picture of it here, where we have diffraction patterns, right, on a screen. This one down here is a good one, down way at the bottom here. Circle that in yellow. This is a really good example of the separation of the dot patterns due to diffraction. Now, these were all created by one source of light that went through this thing called a diffraction grating, right? Let's change colors again here. A diffraction grating, which has these openings, right? The openings allow the light source through, right? It creates separate light sources on the other side, and these light sources then go out in these semicircular fashions, right? And then they meet and they either add up together or they destroy each other, or there's in-betweens as well. Okay, so this is the result of diffraction. We get these patterns. Okay, so since this is physics, we have to ask ourselves, well, is there an equation or is there some way to analyze this so that we can figure out what kind of patterns we're going to see based on the number of openings, the width of the openings, the wavelength of the light, things like that? Of course, the answer is yes, right? And so what I'd like to do is show you how we can determine what that equation might be. And it turns out to be a fairly simple equation, a good way to analyze. But what we want to do first is take a look at a couple of light waves as they go through a diffraction grating. So over on the left-hand side, this is a diffraction grating, right? A diffraction grating with just two openings, okay? And there's a distance d between the two openings, and we're going to use that in a bit. We've also placed a screen at some distance L from the diffraction grating. And over on this screen, I'm going to get minimums and maximums. And I'm really concerned mainly with the maximums here. All right, so I'm going to get some dot patterns, say here, and here, and here, and then again down here, and here, and here, due to the different patterns of light adding up and constructively and destructively. So let's just take a look at two of the light waves. So we have a red ray of light up at the top, we have a blue ray of light at the bottom, and they are coming through, and you'll notice that they are in phase with each other. So as they get through the opening here at the bottom, and as they go through the opening at the top, we have peaks. Both of the waves are at a peak, and they're both the same frequency because they're both coming from the same light source, okay? And so they should stay in phase all the way until they get to this point way out here. And what are they going to do way out there? they're going to constructively add. And so when they get out here, they're going to constructively add. We're going to get a bright dot of light. Okay, and this area right here, that dot right there, is called the central maximum. Okay, maximum. Oh, I forgot 2 letters. Okay, central maximum. And then we're also going to get dots to the north of the central maximum and to the south of the central maximum, or up and down. And these dots are called fringes. Okay, so we have fringes up above the central maximum. We have fringes below the central maximum. And we give those fringes numbers. So if I count up from the central maximum, and I give the central maximum a number of 0, the first dot that I see above the central maximum will have a number of 1. The second will have a number of 2. The third will have a number of 3, and so on and so forth up the line. Below the central maximum, we'll do the same thing. The first dot will have a number of 1. The second will have a number of 2. The third will have a number of 3. And if there are more, we just keep on counting. And we use those numbers. Okay. All right. So let's scroll down a little bit here, knowing what we know. So now let's say we not only have our central maximum dot right there, but I'm going to change colors here as well. So I'm going to change this to orange. We have a central maximum dot there, but we also have a fringe dot up here. And we could have multiple fringe dots. So I'll just color some of these in. And they're approximately spaced, the same spacing apart. So this would be the n equal 1 to the third order fringe up there. Now, what has to be true in order for us to have a bright dot up at the top? Well, in order for us to have a bright dot, the waves have to be in sync when they hit. So it's got to be a peak and peak or trough and trough. But either way, they've got to be in sync. Okay? But if you'll notice, the distance that it's going to take to get from the top opening here up to this point for this ray of light, the red ray of light, is going to be different than the distance that it's going to take for the blue ray of light to get up to this point right here. The distances are going to be different. But since the two light waves have to be in sync or in phase, what has to be true about the difference in the distances? Well, they've got to be an integral number of some light waves apart. So this distance d, the delta here, the difference in distances, has to be, right, if this is the difference in distances right here, all right, that distance difference has to be lambda or some multiple of lambda. It's got to be a whole number multiple of lambda starting with 1. It could be 1, could be 2, could be 3, could be any number. But it's got to be some multiple. I've used the number n here. All right, and n corresponds to the fringe numbers. Okay. Oops, don't want to move that. All right. So the difference in distance has to be an integral multiple of my my wavelength. Okay, so that's part of what we need to know. The other thing we need to know, and I'm just going to erase a little bit here, just to make this a little bit clearer, although I did not mean to erase all that. Let me draw this back in here, if I may. I did not mean to erase all that. Okay, so we'll do that. And so I'm redrawing my triangle, and actually this should be down here. So see, can I select that? I'm going to move this down here some. That's not going to let me do that. All right, let me just draw it in like this. I did it again. Oh, Magoo, you did it again. Okay, so there's our triangle. All right. Over here, we've got a hypotenuse, all right, and we have a right angle right here, right in here. Okay, well, I have an angle theta, all right, that describes this triangle. So this angle is angle theta in here, and it just so happens that this angle in here is also theta. So I have similar triangles. Well, if this angle in here is theta and this angle out here is theta, perhaps I can figure out just what the difference is here, right? And I can write a different equation that would help me out here. Well, if I want to know what this side is here, and I happen to know the distance between my openings, right? Because remember, the difference between the openings here is the hypotenuse. Okay, so I have the hypotenuse of a triangle. I've got this adjacent side, and I want to know the opposite side, because this opposite side down here is the difference in the distance between this opening and up here and this opening and up here, right? It's the difference between the two openings and this point way up here. I'd like to know that distance, right? I'd like to know what this distance is right there. Well, the sine of an angle is equal to the opposite side divided by the hypotenuse. Okay, well, the opposite side then is equal to the hypotenuse times the sine of the angle. Okay, well, the hypotenuse in this case is the letter d. All right, so d times the sine of theta, okay, is going to equal this difference in the distances here, okay, between the red wave and the blue wave. Well, I already said that the difference in the distances between the red wave and the blue wave has to be n lambda, has to be some multiple of the wavelength. And so what we end up with, is this distance here, right, this difference in distances here, times, is going to be equal to d, right, the distance between the openings, times the sine of theta, times n equals n times lambda. I'm sorry, let me restate that. D sine of theta will equal n times lambda. D being the distance between the openings, right? Lambda, or theta, I'm sorry, theta being this angle in here, but also this angle right in here, and I apologize because this is getting all messy here. And that's going to equal n lambda. So this is an equation that we can use to solve for a variety of things. So what are all these things? Let's go back up. Let's move, this back up here a little bit. Okay. So my equation that I have is d sine theta equals n lambda. Well, what is lambda? Lambda is just the wavelength of the light, right, incident to the two openings. That's easy enough. What's n? N is simply the number of the fringe, right? Is it the first dot, the second dot, the third dot? What is it? Okay, that's all n is. Okay, what's theta? Theta is this angle in here. Okay, that's all that that angle is. And d, well, d is the distance between the slits or the openings. Okay, these are all things we can measure or we can figure out, all right? And so we're going to be doing that in a few minutes. So this is the explanation as to how we achieved the formula for diffraction, all right, for constructive interference. So this is the formula for finding bright order fringes on our screen. And we're going to do some examples in one of the other sessions. So stay tuned. I'll be doing some examples, and I hope this helps a lot.